Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Electron Probe Microanalyzer, that is EPMA, under the paper Characterization of Materials 1. So students, let us see what we are going to learn in this module. In this module, the working principle of electron probe microanalyzer is described. Then, the instrumentation of EPMA is discussed in detail. After this, the limitations and strengths of electron probe microanalyzer are studied. The sample collection, preparation, and data collection is also described in this module. Let me first introduce you to electron probe microanalyzer, which is also abbreviated as EPMA. Casting, he established the basic principles of quantitative EPMA. The first commercially manufactured electron microprobe in the year 1958 was made available by the French company EPMA. It is also known as electron microprobe or simply probe. It is non-destructive analytical technique. It is a microbeam instrument. It determines the local composition of solid samples. Basically, its working is same as scanning electron microscopy with additional ability of chemical analysis. It provides detailed X-ray mapping of composition contrast. Let us discuss the working principle of electron probe microanalyzer. When the probe or electron beam strikes the specimen, repeated interaction between electrons and atoms of the specimen occurs till they come to rest or emerge out from the specimen surface. In the kilo-electron-volt energy range, the expected interactions of electrons with atoms are scattering, either elastic and inelastic, and Bremsstrahlung emission. Elastic collision is the phenomena in which both the states of the atom, that is, initial and final states, remain the same, which is generally the ground state. In this case, the direction of movement of electrons is changed. Inelastic interactions are the phenomena wherein the atom is promoted to an excited state. That is, a share of the electron's kinetic energy is given to the electrons of the atom. This interaction comprises A. the electron's excitation in the bands, which is maybe either valence or conduction. B. plasmonic excitations. And C. ionization from the inner shell of atoms, that is, the production of a vacancy in an inner electron shell, which is shown in figure 1. After initial ionization, the atom de-excites by migrating the vacancy to the outer shells via repeated electron transitions and releasing the energy as characteristic X-rays or Auger electrons. Initial ionization is thus responsible for the generation of characteristic X-rays. Bremsstrahlung emission occurs when the electron is decelerated in the desired atom's electrostatic field. Bremsstrahlung emission has almost no effect on the electron trajectories. However, it causes a constant background in the X-ray spectrum. Emitted photons as characteristic X-rays or as brimstone originate at sample depths extending from the surface to some maximum depth, which is governed by the material and on the incident electron's energy. Generated X-rays first interact with the atoms of the specimen before emerging out of different mechanisms, mainly through photoelectric absorption, and as a result, fluorescent X-rays may be emitted. We next discuss the instrumentation of electron probe microanalyzer, that is EPMA. Electron microprobe analyzer includes four main components. First one is the source of electron. Second one is the electromagnetic lenses. Third is the sample chamber. And fourth is the detector. The schematic diagram of a typical microprobe is shown in the figure. As could be seen in this figure, the source of electrons is electron gun, which is generally a thermoionic gun. This thermoionic gun is usually made up of tungsten or Lab6. Electrons are produced by thermoionic emission phenomena, that is, by heating the tungsten or Lab6. Power supply is used to keep the filament potential negative to accelerate the electrons through aperture from the filament. Accelerating voltages are used to accelerate electrons towards anode and lies in the range from 1 kilovolt up to 40 kilovolt. Focusing of electron beam on the target is done by using electromagnetic lenses with a final diameter of about 0.1 to 1 mm, and the electron current is also controlled with it. That is, the number of incoming electrons per unit time, and can assume values usually in between 1 to 300 nanoamperes. Faraday cup is used to measure electron current, which is stabilized with the beam controller apparatus. Electron conductivity is confirmed when the sample is connected to ground. To overcome certain complications such as filament oxidation, acceleration voltage breakdown, and electron scattering in the beam by residual gas, a standard high vacuum technique is designed to minimize the carbon contamination at the point of electron impact due to cracking of hydrocarbons present in the chamber. The electron microprobe is fitted with a liquid nitrogen, or I can say cold finger, near the sample and directing an air jet in the direction of electron impact. Microprobe analysis have a distinctive feature of placing an optical microscope coaxially to the electron beam to find the desired sample area, for which sample can be scanned with the beam analogous to conventional scanning electron microscopy. Eventually, images are generated by recording the secondary, that is SE, and the backscattered electrons, which are BSE, emitted from the target and are captured by the electron detector. Wavelength disperser spectrometer comprises a crystal monochromator and X-ray detector, which is oftenly a gas proportional counter. The arrangement is made in a way that incoming X-rays are deflected as per Bragg's conditions, and some of them are recorded by the detector. The Bragg's law follows that N lambda is equal to 2D sine theta, where lambda is the wavelength of X-ray and n is the order of diffraction. D is the gap between the planes of monochromatic crystal and theta is the angle of incidence of the X-rays. Using the flat surface of crystals as well as point sources of X-rays, Bragg reflection ensures only a small part of the crystal. This reflection is enhanced by placing the target, crystal and detector on the focal plane of a circle whose radius is capital R, which is also termed as Rowland circle, and bending the crystal atomic planes to a radius of 2 times R. This focusing geometry is called the joint type. This organization keeps the incident X-rays angle constant above the line which is demarcated by the intersection of both, that is, the plane of Rowland circle and the crystal surface. The crystal as well as detector is timely rotated mechanically to record the spectra of X-ray as a function of wavelength. In the case of focusing geometries, the distance between source and crystal is proportional to sine of q and consequently proportional to the wavelength. Thus, the crystal is simultaneously rotated and moved along a straight line via mechanical connection. Lithium fluoride, pentaerythritol, pentaerythritol, PET, and thallium acid phthalate (TAP) crystals are utilized for microanalysis. The wavelength range covered by using these three crystals is lambda of the order of 1 to 24 angstrom. For longer wavelengths, layered synthetic multistructures comprising of numerous interchangeable sheets of high and low atomic number materials such as tungsten oblique silicon, nickel oblique carbon, and molybdenum oblique boron carbon are used. For these situations, D is equal to the total thickness of one layer pair of both high and low atomic number material. The gas proportional counter consists of a tube filled with gas and fitted with a coaxial wire which is maintained at a 1 to 2 kilovolt potential in comparison to the tube's outer wall. By photoelectric effect, these X-rays entering from the window get absorbed by the gas molecules, thereby producing free photoelectrons which in turn are accelerated via electric field. Consequently, an avalanche of secondary electrons is generated. As a result, pulse produced by every incoming X-ray has a height directly proportional to the energy of X-rays. These pulses are further sent to a pulse height analyzer, that is PHA, whose purpose is to count pulses having desired height, which is generally comprised in a specific voltage window. The values of counter high voltage, gain and discriminatory settings, that is baseline and window, are selected by PHA display. In flow type proportional counter, gas can escape from the window and so must be continuously supplied. Otherwise, sealed type counters should be used. Since WD spectrometers permit only one wavelength recording at a time, therefore, electron microscopes are commonly furnished with several, that is up to 5 spectrometers, which are shown in figure 3 each with several interchangeable crystals. The EG spectrometer utilizes a solid state device named X-ray detector, which is typically a crystal semiconductor like silicon or germanium, which discriminates X-rays based on their energy. Due to improved resolution, WG spectrometers have superior, or I can say lower detection limits than EG spectrometers, which has the detection limit usually 10 times of WD spectrometers. Let us discuss the applications of EPMA. Firstly, geological resources are chemically analyzed at small scales, which is quantitative EPMA analysis. Secondly, it is utilized for analysis of individual phases such as igneous or metamorphic minerals. Other uses include analyzing small quantities of samples or other valuable samples such as experimental run product, sedimentary cement, volcanic glass, matrix of a meteorite, archaeological artifacts including ceramic glazes and tools, etc. Thirdly, for determining the UTH age of a mineral like monazite without evaluating the isotopic ratios. We next move on to study the sample collection and preparation. It is utilized for synthetic material analysis such as optical wafers, thin films, microcircuits, semiconductors, and superconducting ceramics. Secondly, sample is prepared of desired size, that is 27 cross 46 mm rectangular, 1-inch round disc, 30 microns thick. Thirdly, sample is polished to remove surface imperfections so as to avoid interference with an electron beam or sample interactions. Next, the coating is done on many minerals like silicates, which are electrically insulated in order to prevent charging. Carbon, gold, and aluminium are the most commonly used for thin film coating by evaporation method. Coating should be as thin and light as possible such that interference with the electron beam and emitted X-rays can be minimized. Next, the specimens are placed in the sample chamber through an interlock vacuum system and mounted onto the sample stage. High vacuum can be achieved by pumping the sample chamber. Then, the experimental conditions, that is, accelerating voltage, electron beam current, and beam focusing, must be properly selected. We will next discuss about the data collection, results, and presentation. Semi-quantitative EDS analysis is utilized for identifying diverse elements which might be existing in an unknown sample. WTS examinations is primarily involved in the case where composition analysis of an unknown phase is done quantitatively. This is achieved by performing instrument calibration using samples of known composition, subsequently evaluating the results quantitatively in addition to valuation of miscalculations. In a case where 4 to 5 spectrometers exist, 10 to 12 elements can be acquired. Data output contains, after standardization and several data correction procedures which involve background subtraction and various types of matrix corrections, a data table in which simple oxide weight percentage of every mineral is present. Next, discuss the limitations of electron probe microanalyzer. In spite of the fact that electron microprobe could detect or analyze every element of the modern periodic table, one of the demerits is its inability to identify the elements with lowest values of Z, like H, helium, and lithium. Therefore, molecules like example water in hydrous H2O, minerals cannot be examined by this technique. Secondly, overlapping peak positions of X-rays produced by means of both energy and wavelength in some elements should be separated. Third, microprobe examination is described as elements oxides, not by means of positive ions, that is cations. Thus, cation proportions and mineral formulae needs to be calculated while considering the stoichiometric rules. Last, as this microprobe analysis is unable to differentiate among the various equivalent states, therefore, ferric or ferrous proportion cannot be obtained and should be assessed by other methods. Let us discuss about the strengths of electron probe microanalyzer. A great similarity is there in between scanning electron microscopy and electron microprobe. However, the only difference is that electron probe is provided by a variety of crystal spectrometers which allow chemical analysis quantitatively, that is WDS, with high sensitivity. EPMA is fundamental in chemical investigations of various solid substances at small spatial scales, that is, about 1 to 2 micrometers in diameter. Thus, this technique can also be used to study minute single phases such as minerals in any material such as rock with spot examinations. Spot chemical analysis can be obtained in situ, which allows the user to detect even small compositional variations within textural context or within chemically zoned materials. Electron probes usually employ an array of imaging detectors, that is SEL, SEI, BSC, and CL, for creating images of the surface and internal compositional structures to help with investigations. So students, let us now summarize what we have learned in this module. In this module, the working principle of electron probe microanalyzer was described. Then, the instrumentation of electron probe microanalyzer was discussed in details. Then, the sample collection, preparation, and data collection was also described. Finally, the limitations and strengths of electron probe microanalyzer were studied. Thank you, students, for your attention.